Well, hello there. Let's do some op-amp. Let's do some op-amp circuit analysis. So if you remember from the last lecture, this here is one way to model an op-amp, and it lets us include some of the non-ideal effects, but we're not going to worry about those. We're just trying to do the basic op-amp analysis using an ideal op-amp that has all of these parameters. Infinity gain, open loop gain is the big one. So the system we're going to use for all of our circuit analyses is to have the op-amp like this and our two op-amp rules. The first rule is that because there's feedback in the circuit, the two input voltages will be the same. So VP here and VN will be the same voltage. And the other rule is that the current into the op-amp is 0. So no current here and no current here. The rule does not say anything about the current coming out. That's not 0. So we don't know what it is. But with these two rules and regular node analysis, we will get enough equations to solve the system. So this is what you need to be good at for the homework, and this is what we're going to practice. So here is a circuit called a summing amplifier. We've got our two voltage sources, V1 and V2, each connected with a resistor to the inverting input, the minus input here, and the non-inverting input, the plus side, is connected to ground. So we know that the input voltage here is 0 volts. That means that Vn must be 0. That's from our golden rule or our summing point constraints. And so then we can do Kirchhoff's current law at this input node. Always basically do Kirchhoff's law at these two nodes and hope for a solution. So if we do Kirchhoff's current law here, assuming that Vn is 0, because Vp equals Vn and Vp is connected to ground, it looks like this. So Vn minus V1 over R1, that's the current going out on this branch, plus Vn minus V2 divided by R2, current going out on this branch. 0 minus V0 over Rf is the current going out on that branch, and those have to sum to 0. And we've just got one thing we're solving for, V0 or V out, in terms of the two inputs, so we can write it like this. V out is negative Rf times V1 over R1 plus V2 over R2. So we see we have the sum of the two voltages here. There's also a scale factor set by the resistors. And if you wanted to not have a scale factor, you could make all the resistors the same. They would cancel out. And there's a minus sign here. So you do have to keep track of these minus signs. This is a negative voltage if V1 and V2 are positive. So in a block diagram form, we have V1 coming into our system with a gain of negative Rf over R1, and V2 comes in with a gain of negative Rf over R2, and they get added together to get the final voltage. So this is the summing amplifier because it adds them together, but it does flip the sign. So if we wanted to use that in some example, here is what we're doing. So remember, op-amps are to do math. So often we have some math equation we're trying to implement. So we want V out to be 4V1 plus 7V2. So you can see we're adding and scaling. So this summing amplifier makes sense here. And then to get rid of the minus sign, we will put after the summing amplifier an inverting amplifier with a gain of 1. So the block diagram is probably the easiest thing to see here. V1 times minus 4 plus V2 times minus 7 gives us the negative of the equation we want. Add them together and put the minus sign in here to get the positive that we want. So we need negative 4 here and negative 7 here and negative 1 here. To pick the resistors, we can choose things. We know the ratios here, so we can pick one normally to be whatever we want and then solve for the others. So that's what's done here. there's often some arbitrary choices to make in terms of the scaling. If we have the ratio here, RF1 could be 4 and R1 could be 1, or 4,000 and 1,000, or 4 million and 1 million. So you have some choices, a lot like the voltage divider equation when we did that back then. And in theory, it doesn't matter, but normally you pick something in the kilo ohm range to be good numbers. Here's another circuit to analyze using our same process. This one's a little more complicated because both input nodes have sources and resistors connected, so we have to analyze them both. So again, we take a look at the circuit and do Kirchhoff's current law at these two nodes and hope for a solution. If not, we would move out to the other nodes in the circuit. So starting with the Vn node, we have Vn minus V1 over R1, that's I1 here. Vn minus V0 over R2 is our I2. Vn over here, we can't do Ohm's law. Remember, we can't do Ohm's law because there's no resistor here, so we have In, but from our golden rule, or our summing point constraint, In is 0. So we can write it like this. Similar thing for Kirchhoff's current law at the non-inverting input node, Vp minus V2 over R3 plus Vp minus 0 over R4, these two terms, and then Ip, can't do Ohm's law, but that one will go to 0 when we apply the ideal op-amp constraints, the summing point constraints, or the golden rule. Ip equals In equals 0, that zaps this term and this term. Vp equal to Vn gives us, basically we have three equations, 1, 2, and this would be the third one, and three unknowns, V out, Vn, and Vp. The easiest thing is probably to back substitute Vp equals Vn into these two and solve it 2 by 2, but however you want to solve it, if you combine them together to eliminate Vp and Vn, we get this equation for V out, and it's got this thing based on the resistors, this big scale factor here, times V2 minus R2 over R1 times V1. So it's a subtraction. This is positive, this one's negative, and that gives us RV. So again, this is the equation we solved for, and notice the minus sign, that's why it's a difference amplifier. And in block diagram form, we have V2 coming in, gets multiplied by this scale factor, this gain based on the resistors. And we have another gain here, R2 over R1 with a minus sign that goes in here, and then they add together, and we get the output. So if you can follow this, if you could solve this one, then you're doing great, and you've learned what you need to know for op-amp analysis. Here's another example where we're trying to do a elevation sensor. And I was really happy to see this when I went through these slides. These are slides from the textbook. But the very first op-amp circuit that I ever analyzed was an altimeter for a drone, because I worked for a drone airplane company, and we had to do something really similar to this, where the altitude, or the pressure, it was a pressure sensor, but the pressure gets lower the higher you go, had an output here, and we needed to amplify it into a very small band because it was a pressure sensor for weather, and the altitude change is very small compared to what weather can change. So anyway, I worked on something really similar to this. So we have this equation for the sensor response in terms of altitude, and what we want is the voltage to directly correspond to H. So we want to solve for H there. So we do that, then we know that V out needs to be 5 times Vs minus 10. So we need to scale the output voltage of this sensor. So this is the sensor's voltage output. We need to multiply it by 5, but then we would get this big offset. So we need to subtract 10 to make it back to output equal to the altitude. So this is a scaling and a subtracting kind of circuit. So here is an op-amp circuit that we just looked at with this setup here, and we want 5Vs minus 10. So we want equation 449, this one, to correspond to this one. So this needs to be 5 and this needs to be 10. So they've picked voltages, and again there's some degrees of freedom, but start with the easy one. We need R2 over R1 equal to 10, and we have a V1 in there too, so we need to attach a fixed voltage here. So we can pick R2, R1, and V1 so that they come out to 10 volts. And then once we picked R1 and R2, we can pick the rest of them to make sure that this has the factor of 5. So this is a set. Again, it's not a unique solution. Most of these don't have a unique solution, but picking something in the kilo-ohm range is usually pretty safe. You wouldn't want to pick, you know, 1,000,000 volts for V1. 1 volt is a nice, safe number. You might have a 5-volt supply or a 3.3-volt supply, so picking something that you have handy on your circuit is another way to go. This last op-amp circuit is seemingly useless, but it shows up a fair amount. It's called a buffer, or voltage follower. And what it is we have the op-amp here, and the output voltage just is tied directly to the inverting input, and that's not connected to anything else. And so the analysis is basically using the rules that we have. Here we have no current coming in, so Vp is going to equal Vs. If we did Vp minus Vs over Rs equals 0, so Vp equals Vs. We did that on an earlier analysis. So we know that this is Vs here, and Vp and Vn are the same because of the circuit analysis. So Vp equals Vn, so this equals Vs, and this is short-circuited to the output. So the output Vo is the input, Vs. So whatever you put in here, you get out here. So it seems like a useless thing, because if you just connected this to here with a wire, that also gives you the same voltage. So the reason you use that is shown here. If you have a load, if you have to provide more current, we did load analysis, load error analysis with voltage divider circuits, and sometimes a buffer is used on a voltage divider. Here we have two resistors in series, so the output voltage here depends on the load resistor and the series resistor here. But if we put the buffer in between, then the output voltage is always the input voltage. So the voltage follower, very simple to analyze and surprisingly useful. Okay, so here are the circuits we've looked at so far. We've got the non-inverting op-amp, the inverting op-amp circuit. So these are all circuits. Inverting summing, difference amp, the buffer, and another summing that's not an inverting summing amp. So we have a lot of different circuits, and there are more if you look up some of the, I put a bunch of PDFs on our website if you want to look at some cookbooks of op-amp circuits. But this is generally how you do op-amp circuit design. So you know the equation you want, and then you look in a cookbook for the appropriate circuit. Just to show other things that we're not really going to cover, but you might be interested in if you like op-amps. This is a very common thing to use several op-amps in a circuit to do more math operations. So if you have to do a complicated equation, like we saw with the inverting amplifier after the inverting summing amplifier to make the voltage positive again, a lot of cases you need to use multiple op-amp circuits to get the right equation. So we won't go into what this one does, but you could analyze it in the same way. You get a set of equations for each of these, that this node equals that node, and so forth. And a common use for 3 op-amps is this thing called an instrumentation amplifier, and it's a useful one mostly because it compensates for some of the non-ideal factors, which we're also not going into in this class. So if you can do the basic analysis that we've seen for those circuits that we did so far, then you've learned what you need to learn. We'll see the instrumentation amplifier in instrumentation and measurement systems next fall, But this one is a 3 op-amp circuit, and it has some nice properties for non-ideal properties of op-amps, and you get a basic difference voltage amplifier. So V2 minus V1 times this gain that's set by these resistors is what this circuit provides. Okay, so again, there's some summaries, and you can look in the book for where these circuits and equations came from. We looked at the ideal op-amp properties, the circuit with the non-inverting, inverting op-amp, summing and differencing amp, the buffer or the voltage follower, and the instrumentation amp is a 3 op-amp circuit. If you look into chapter 5, they do circuit analysis with resistors and capacitors, which adds a differential equation term to our analysis, and then you can do things like integration and differentiation. So here is a op-amp circuit that has a capacitor in the feedback path, and the equation for this circuit is V out is the integral of the input voltage. So this is an integrator. You can also do derivative op-amps. And in chapter 7, they do phasors with op-amps, so where the input voltages would be AC circuits. And again, you can use the same rules and just extend them with impedances and do phasor op-amp analysis. So that would be our next step, but we're out of time. These are the last lectures of our class. So hopefully you've learned enough about op-amps to get the homework done, and we'll call it good. All right, well, that's going to be it. So let me know if you have any questions, and I'll see you in the Zoom lectures.